All right, here we are back at our funky spiral curve. Remember, this is the one that if I project down onto the XY plane, looks like this. And then we kind of spread it out as a spiral. And then we had those pink unit tangent vectors at several points along the curve. So now you also have green and blue vectors kind of tail to tail with the pink unit tangent vectors. All right, so each one has a green one and a blue one. I want to focus on the green ones. All right, so the green vectors you'll see are all orthogonal to the pink vectors at each point, and they kind of point inward to the curvature of the curve, right? So the green, we got the unit tangent vector, and then the green one orthogonal, but sort of pointing inward on the curvature of the curve. So those green vectors are all called the normal vector. Those are also unit vectors. And then the blue vector is orthogonal to both the green and the pink vectors. All right, and that one is called the binormal vector. All right, so why do we want this normal and binormal vector? Let me hop over to the one that we did in our example last time, finding the unit tangent, and I'll show you what the normal and binormal do for us. All right, so here is our curve from the last video example. X equals 3 cosine t, y equals 3 sine t, and z equals 4t. And we can see that unit tangent hugging the curve as it slides up and down. That's the vector valued function that we calculated in the example. All right, so I mentioned the normal vector is going to be orthogonal to that pink vector. All right, and as it slides up and down the curve, that normal vector is going to point towards the inward of the curvature of the curve. You can see it just kind of follows the twistiness of the curve as it goes down along the curve. And then the binormal vector is going to be that blue vector that's orthogonal to both the tangent vector and the normal vector at the same time. All right. So what do the normal and binormal do for us? If we find the plane that goes through the normal and the binormal, which is going to be here, this might be kind of hard to see. All right. This gives us a plane that is orthogonal to the curve at every single point. Okay, if we use the plane that goes through the normal and the binormal. All right, so how do you calculate these very important normal and binormal vectors for any vector valued function? Well, you got to start off with that t vector function that we learned how to calculate in the last video. Remember that t of t, we started off by taking the derivative of the vector valued function and dividing by its magnitude. All right, and we had this one beautiful example where that magnitude in the bottom just boiled down to the number 5, and it was really sweet and easy. Most vector valued functions do not have a sweet and easy magnitude of their derivative for down in the bottom. So usually that magnitude in red down there, r prime of t, is filled with square roots of a mess. All right. And then you turn around to find the normal vector, you need to take the derivative of this fractional function with the square root of a mess in the bottom. It's a pain. And then after you're done taking that derivative, you then have to find another magnitude. So you're going to have these nested square roots and fractions in there and lots of quotient rules and chain rules. It is really difficult for most vector valued functions. For that one sweet one that we had, it wouldn't be too bad. But for most of them, this is a hot mess. All right, and then once you're done with that, how do you calculate the binormal? Remember, the binormal is orthogonal to both the tangent and the normal. You get that by crossing those two vectors. Remember that crossing two vectors gives you a third vector that's orthogonal to the two original vectors. All right, so while these two vectors are incredibly important, they are usually too much of a mess for us to calculate with just pencil and paper. So we are going to appreciate that they are important, appreciate GeoGebra for animating us that nice plane, and appreciate that we could do this if we had all the time in the world and then not do it. See you in class.